Hi everyone, we're going to continue talking about empirical formulas as we explore different ways to use the new values that we've been working with, which is the mole, and starting to look at the periodic table a little bit more. And when we talk about empirical formula, what we're really talking about is just the simplest or the smallest whole number ratio of atoms that are within a compound. So as an example, we can look at this is the formula for acetylene, C2H2, and this is the formula for polystyrene, which is a form of styrofoam, C8H8. But both of these can be narrowed down, or I should say simplified, to CH, C1H1. So if we were looking at the empirical formula, they would have the same empirical formula, but these are what we call their molecular formulas are different. And we're going to explore how to identify what the empirical formula is, and then we're also going to look at how can we take the empirical formula and with a little information create or determine what the molecular formula is. Now, all the formulas that we've been looking at so far this year are molecular formulas. So something like CO2 or H2O, those are the molecular formulas for that particular substance, whether it's carbon dioxide or water, or if it's NaCl for sodium chloride. The molecular formula will tell you the actual amount of each of the atoms that are in that particular compound, whereas the empirical formula is simply going to show us what the ratio is of one element to another within that compound. So a lot of compounds can have the exact same empirical formula. So when we want to try to differentiate between different substances or what the properties might be, looking at their empirical formula isn't actually very useful. It's the molecular formula that we would need then in order to determine what the identity of the actual substance is. The molecular formula is what will determine the properties. The empirical formula simply determines the ratio of the elements within that compound. So experimentally, you may have been able to only discover what elements are in a compound. It's not going to tell you what the formula is. It's not going to tell you the exact way that those particles are arranged. So sometimes if we were able to break something down and determine which elements were in there and in what proportion, we can use that data to help us identify what the actual molecular formula is. But in order to get that, we're going to need the empirical formula first. So using that data, that mass data, and the molar mass of an individual element, we can determine the molecular formula, and then that molecular formula again will be important for determining what the compound's properties are. So once you determine that molecular formula, we know the more details about the specific makeup, how the particles are arranged in accordance with one another, and then how they're arranged within a particular molecule or formula unit, depending on what type of compound it actually is. So let's say that you either on your own or are given some data that says that an unknown substance turned out to be 67.6% mercury, 10.8% sulfur, and 21.6% oxygen. What would the empirical formula of this substance be? So this is an example of a problem that you guys will have to start working on, and I'm going to show you step by step how to go through this problem. And at the end, we will have our empirical formula for this particular compound that's made up of these three elements here. The first thing you're going to want to do is assume that you have 100 grams. It's always the easiest to take percents and just say, let's assume we have 100 grams of this, because if I have 67.6% mercury and I had 100 grams total of the sample, then I know very easily that I've got 67.6 grams of mercury and then 10.8 grams of sulfur and 21.6 grams of oxygen. By having the percents converted to grams, it's going to allow us to do our next step, which is going to convert each of the substances that we're given into moles. And so we need to do that for each of the elements. So this is going to rely on a basic mole conversion. We're going to go from grams to moles. And if you remember from what we've been doing the last couple of days, in order to do that, we're going to utilize the molar mass on the periodic table for each of these elements. So for mercury, if we had 67.6 grams of mercury, we're going to set that up by showing our molar mass as our conversion factor. So for every 1 mole of mercury, we have exactly 200.59 grams of mercury. That would come directly from the periodic table. And we're going to do the same thing for each of the other two samples here. So the sulfur and the oxygen that were also found in that compound. Once we have all three of these, we're going to be able to determine what we call the mole ratio is. What is the ratio of moles of mercury to moles of sulfur to moles of oxygen? Now don't forget, the reason that we're doing this is because what we're looking for is an actual formula, which is going to show us the number of particles of one type of element that are compared to the number of particles of another type of element. Mass does not tell us that. We can find the percent or the grams all day long, but that won't indicate how many actual particles there are. So when we convert from grams to moles, remember the mole is simply a way that we can look at the number of particles that there are there in that particular substance. And when we can compare the number of particles of mercury to the number of particles of sulfur to the number of particles of oxygen, that will help us figure out what is the simplest arrangement of these three to each other. So in order to find the mole ratio, we're going to take whatever the smallest value is. In this case, it's 0.336. And we're going to divide each of these numbers of moles by the smallest number of moles. So 0.336, we're going to use this one for sulfur because it is the smallest. And so everything is going to be determined based on one unit of sulfur. Because if we take each of these divided by 0.336, we're going to get 1 mole of mercury approximately. We're going to get approximately 1 mole of sulfur. And we're going to get approximately 4 moles of oxygen. Now, if your numbers don't work out exactly, if you don't have exact whole numbers, if it's very, very close to a whole number, then we can assume that we are either going to round slightly up or slightly down. Like I wouldn't get exactly 1 for this, and I didn't get exactly 4 for this, but I'm going to use 1, 1, and 4. Remember that we're doing this because this is going to, again, determine a number of particles, and we can't have partial particles. So now that we have the number of moles that we've determined in our mole ratio, so we have 0.336, 0.337 and 1.35 moles. But what is the mole ratio? So that says that for every 1 mole of sulfur, we have exactly 1 mole of mercury. And for every 1 mole of sulfur, we have exactly 4 moles of oxygen. So this ratio is really what is the most important thing. So by utilizing these three numbers, the ratio of oxygen to sulfur to mercury, we can then determine what the empirical formula is, simply by saying that we know that for each one of these, let me go back to this really quick. So step 4 is going to be to actually write the formula with the atoms going in order from the most metallic to the least metallic. The number of moles becomes the subscript then in that formula. So how do you determine if something is most or least metallic? It's going to depend on the position on the periodic table. So things to the furthest left are the most metallic. Things to the furthest right are the least metallic. So mercury is further left than sulfur or oxygen, so that would go first. Sulfur and oxygen are right above each other. Oxygen just one above sulfur. So how do you determine which one's furthest left? Well, they're the same distance left, and so then the one that's closest to the top is the least metallic. So we're going to do mercury, sulfur, and then oxygen. So we have 1 mercury for every 1 sulfur for every 4 oxygens. So this then, mercury sulfate, or HgSO4, is the empirical formula. That is the simplest ratio of mercury atoms to sulfur atoms to oxygen atoms in this particular compound. We're going to continue to use these in order to work on some more calculations and take the examples that we had here and go from empirical formulas to molecular formulas, but that will be in another day. So hopefully this helped. If you have questions about this, please come and see me.